Black holes, right. They're like these ultimate cosmic traps, where even light can't escape. But what if, and this is where things get really interesting, what if that's only half the story?
Yeah, it really is fascinating when you think about it.
So, like we're going to unpack today, Einstein's revolutionary math, it kind of hints at something far more bizarre.
Way more mind-bending, for sure.
These so-called dead ends, these black holes.
They might actually be connected.
Yeah, connected to, like, other parts of the universe.
Or even, get this, other universes entirely.
Crazy.
Absolutely, it's mind-blowing stuff.
Okay, so in this deep dive, we're going deep right into these incredible ideas.
White holes, parallel realities, those theoretical bridges between them, it's all on the table.
We've got a stack of sources here, some fascinating stuff. About the bizarre things you'd actually see if you were, like, falling into a black hole.
To, like, the maps physicists use to navigate the fabric of space-time itself, it's amazing.
So our mission, if you want to call it that, is to explore these concepts together. We'll pull out the most intriguing insights and try not to get lost in the complexities.
It's easy to do, for sure.
It is. So we'll start with those strange predictions about what happens near a black hole.
What would you actually see?
Yeah, exactly. And then we'll venture into some of the wilder implications of Einstein's work.
Possibilities of cosmic connections, all that good stuff.
Right. All while keeping our perspective grounded in what we actually know. Or, well, what science currently understands.
Yeah, I mean, it's theoretical physics, right? We're dealing with the edge of what we know.
Exactly. It's exciting, though, right? I mean, the possibilities.
Oh, absolutely. When you consider the full implications of Einstein's theory, it's not just about incredibly dense objects.
It opens these, like, theoretical doors.
Doors to concepts that honestly sound straight out of science fiction.
It really does. So we're talking white holes, connections to other universes.
Maybe even pathways between them, like wormholes. Imagine that.
It's, like, mind-blowing. Okay, so let's jump right in. Let's dive into, well, a truly counterintuitive idea.
Okay, I'm intrigued.
What would you actually see if you watched, like, something fall into a black hole?
Oh, that's a good one.
Right. Forget the Hollywood stuff.
Right, the special effects, the...
All that.
Yeah, the reality, based on what Einstein's work suggests, is far stranger. Much stranger.
Way stranger.
Way stranger, yeah. Okay, so imagine this. You've got your astronaut bravely heading towards the event horizon of a black hole. What would you see if you were watching from a safe distance?
I mean, wouldn't he speed up because of the crazy gravity? That's what you'd think, right?
It's the opposite, actually, and this gets to the very nature of space-time. You'd see him slowing down as he gets closer and closer.
Really?
Yeah, almost like he's moving through, I don't know, like thick molasses or something.
That's so weird.
It is. And it gets weirder. It's not just his movement. Even the light he's sending back to you. Like, imagine an SOS signal. That would appear to slow down, too.
Yeah.
It's like time itself is stretching and compressing around him as he gets closer to the point of no return.
So time's not constant, like it's relative.
Exactly. And this is where we see how gravity, according to Einstein, warps space-time. And I mean, really warps it. It affects not just objects, but the light itself. The light emitted by our falling astronaut has to fight against this immense gravity to even get back to you.
So it gets stretched out, like, does that change the color or something?
It does. Its wavelength gets longer, shifting towards the red end of the spectrum. It's called redshift. And eventually it would shift so far that we couldn't even see it anymore.
So, like, it would just disappear.
Basically, yeah.
Yeah.
The light would be redshifted beyond our ability to detect it.
That's wild. So, okay, here's a thought, and this is pretty out there. But theoretically, right, because light can still, like, escape from just outside the horizon, even though it's redshifted like crazy,
Right.
Could you see a frozen image of everything that ever fell into the black hole, like, imprinted on its edge?
I mean, theoretically, yeah, maybe. But there's a catch. Light isn't emitted continuously. It's emitted in packets, photons. So there would be a last photon that escapes.
I see.
And after that, there's nothing more to see. That frozen image, whatever's left of it, would eventually disappear.
So you're saying there's a limit, like, even theoretically?
It seems so, yeah.
Wow, okay. So all this weird stuff, the time slowing down, the light getting stretched, it all stems from this radical shift in how we understand gravity, right?
Yeah, Einstein sparked a revolution in physics. He went way beyond Newton's idea of gravity as a force.
Which, had its own problems.
It did. One big problem was the concept of action at a distance. I mean, how could the sun, millions of miles away, instantly exert a force on the Earth with nothing connecting them? Even Newton wasn't comfortable with that idea.
Right, and he was a genius. So Einstein comes along, right, more than 200 years later, and gives us a completely different picture.
A totally different picture. He said gravity isn't a force that acts across empty space. Instead, it's the curvature of space-time itself. It's caused by mass and energy.
Okay, so space-time, that's not just like a cool word.
No, not at all. It's this fundamental fabric of the universe where space and time are interwoven. And Einstein said that anything with mass or energy warps this fabric.
So like the sun is warping space-time, the earth is warping space-time, even we are, just a tiny bit.
Absolutely. And the more mass of the object, the more it warps space-time around it.
And that's what we experience as gravity.
Exactly.
It's pretty mind-blowing.
Oh, it is. It is. And Einstein came up with these equations called field equations that describe exactly how space-time curves in response to mass and energy. It's like the universe's recipe book for gravity.
A recipe book. Okay, explain that a bit more.
Sure. Think of it this way. You've got your ingredients, mass, and energy, and the recipe book, the field equations, tells you how to mix them together to get, well, the curvature of space-time.
Okay, so you're saying these equations can tell you how space-time is going to warp around anything, any object in the universe.
In principle, yes. But these equations are seriously complex. They're not like your grandma's cookie recipe.
Oh, I was going to say.
People see them written down, and it's often just a single line of symbols. But don't let that fool you. We're talking a whole family of interconnected differential equations, which are a nightmare to solve. They tell us that if we know how matter and energy are distributed, we can figure out how space-time curves. But actually doing that calculation, that's the tough part.
I can imagine. So we have this idea of warped space-time, but to really visualize it, we need to talk about these things called light cones, right?
Yeah, light cones are a great way to picture this. Imagine a flash of light going off in empty space.
Yep.
It expands out in all directions at the speed of light, right? Now picture yourself at the center of that flash. Everything you could possibly experience, everything you could influence, lies within the cone traced out by that expanding light as time goes forward.
So that's my future. Like only things inside that cone can reach me.
Exactly. That's your future light cone. Nothing outside that cone can ever reach you unless it could travel faster than light, which Einstein tells us is impossible.
Right. Makes sense. So what about the past?
Same idea. If you rewind time, there's a past light cone. It represents everything that could have possibly influenced you. Only events within that past cone could have sent a signal traveling at or slower than light that could have reached you by now.
I see. So it's all about what can reach you from the past or what you can reach in the future. It's like our sphere of influence in a way.
In a way, yeah. And we can visualize this with space-time diagrams. We simplify things by looking at just one spatial dimension in time. In flat space-time, the distance between two events, that's not just about how far apart they are in space or time. It's the space-time interval. It's a combination of both. Think of it like trying to meet someone. It's not just about how far away they are, but how much time you have to get there.
So it's like a universal distance.
Exactly. Yeah. But around a massive object, like a star or a black hole, space-time isn't flat anymore. It's curved, remember? So that simple space-time interval equation, it needs some serious tweaking to account for the warped geometry. And that's where Carl Schwarzschild comes in.
Schwarzschild. This guy, he figures out the math, right?
Oh, yeah. He was brilliant. You have to remember, Einstein published his theory in 1915. And even he was having trouble finding exact solutions to his own equations.
So it was really tough stuff.
Oh, yeah. Incredibly complex. Then Schwarzschild, get this, he was serving on the Eastern Front during World War I. And
wow.
Yeah, in the middle of a war, he comes up with the first mathematical description of gravity in these extreme environments. Talk about focus.
That's amazing. I guess sometimes you need that pressure, right?
Maybe. So what he did was simplify everything. He imagined this eternal, unchanging universe, totally empty except for a single point of mass. No rotation, no electric charge, just pure mass. And it's perfectly spherical.
So like a simplified black hole.
Yeah, essentially a theoretical model. And he used spherical coordinates centered on that mass, defined time as measured by an observer infinitely far away, where space-time is flat. And from that, he derived his famous metric.
A metric? Is that like a mathematical description of something?
It is. It's a way to measure distances in a particular space. And the Schwarzschild metric, well, that describes the curvature of space-time outside of that simplified point mass.
Okay, so what does this metric tell us about black holes?
A lot, actually.
Yeah.
It shows that far away from the mass, space-time is almost flat. That's what we experience in our daily lives. But as you get closer, the curvature gets more intense. That leads to the things we associate with gravity. Objects are attracted, and time runs slower compared to an observer far away.
So it's confirming what Einstein said, basically.
Yeah, it's a specific solution to Einstein's equations that shows how gravity works in this very particular simplified case.
Got it. So, but I remember reading that there were some problems with this solution.
You're right. 2 specific problem spots popped up in his calculations. One at the very center, where the distance r equals 0, and another at a specific distance we now call the Schwarzschild radius.
Those are like the trouble spots.
Exactly.
Yeah.
At those points, the math blows up, goes to infinity. It suggests that the theory, as it's described, breaks down under those extreme conditions.
So it's like the math is saying, nope, can't handle this.
Pretty much, yeah. It's a sign that we need a more complete theory, something that can handle those extreme conditions.
Something beyond even Einstein.
Perhaps, yeah. But that's a whole other discussion.
Okay, so back to black holes. What's so special about the Schwarzschild radius then? Why is it so important?
The key thing is that at the Schwarzschild radius, space-time is so warped that the escape velocity, the speed you need to break free from the gravitational pull, becomes equal to the speed of light.
And that's like the defining feature of a black hole.
Exactly. It's the event horizon. Nothing, not even light, can escape from within that boundary.
It's a one-way ticket to, well, oblivion, I guess.
Pretty much, yeah. And initially, a lot of scientists didn't believe these things could exist. They were skeptical.
Really? Why is that?
Because you need an incredible amount of mass concentrated in a tiny volume to create that kind of gravity. They were trying to figure out what happens to stars at the end of their lives.
Right. Stars are these balancing acts, right?
Exactly. You have gravity pulling inwards and the outward pressure from nuclear fusion in their cores pushing back.
Okay.
But eventually the fuel runs out.
So what happens then?
Gravity should win, right?
Oh.
All that mass collapses inward.
Oh, I see.
The question was, how far inward? Does it collapse all the way down to a point? A lot of scientists thought there must be some other force that would stop the collapse before it got that extreme.
Makes sense. So, like, what were they thinking?
Well, in 1926, Ralph Fowler proposed this idea of electron degeneracy pressure. It's a quantum mechanical effect.
Quantum mechanics. So we're going really small here.
Yeah. Very small. The Pauli exclusion principle, which is fundamental in quantum mechanics, says that 2 identical particles, like electrons, can't be in the same quantum state at the same time. So as a star collapses and the electrons get squeezed together, they push back, they resist being compressed further. And that's the pressure that supports white dwarf stars like Sirius B.
So it's like they're pushing back against gravity.
Exactly.
But, like, can they hold back gravity forever?
That's the thing, they can't. Chandrasekhar, he figured this out while he was on a long sea voyage to England. He realized that even electron degeneracy pressure has its limits.
There's a limit to how much they can push back.
Yeah, electrons can only move so fast. The speed of light is the ultimate speed limit. So electron degeneracy pressure can only support stars up to a certain mass. It's called the Chandrasekhar limit. Beyond that,
Boom.
pretty much. Chandrasekhar said that anything more massive than that would have to collapse further.
But people didn't believe him, right?
Eddington, who was a big name in astronomy at the time, he thought there had to be some other way out. He thought it was absurd for a star to just collapse completely.
Nature finds a way.
He thought so, yeah.
But nature had other plans.
It did. For even heavier stars, there's another type of pressure that kicks in. Neutron degeneracy pressure.
Neutron. Okay, so we're going even smaller now.
Even smaller, yep. When a star collapses even further, the electrons and protons get smashed together. They form neutrons. And neutrons, they also follow the Pauli exclusion principle. They resist being squeezed together too.
Okay, I'm following.
And because neutrons are much heavier than electrons, this neutron degeneracy pressure is much stronger. It can support neutron stars.
So are neutron stars like failed black holes?
Kind of, yeah. They're incredibly dense, but not dense enough to form a black hole.
Right. But even with neutron stars being discovered, people still didn't want to believe in black holes, right?
Yeah, the idea of a star collapsing all the way down to a single point, a singularity, it just seemed too crazy, too weird. But in the late 1930s, Oppenheimer and Volkoff, they calculated that there's a maximum mass for neutron stars too.
Like a Chandrasekhar limit for neutron stars?
Exactly. And then Oppenheimer and Snyder, they showed that for the heaviest stars, once they run out of fuel, nothing can stop them from collapsing completely. They said the contraction would continue indefinitely.
So a black hole, basically.
Basically, yeah.
But even Einstein didn't like that idea, did he?
Nope. He was troubled by it. The problem was, according to the Schwarzschild solution, time would freeze at the event horizon from the perspective of someone far away.
Ah, so how could anything ever fall in then?
Right, it seemed like black holes couldn't even form if time stopped at the horizon.
Good point.
But Oppenheimer, he came up with a solution to this paradox. He said that an outside observer would never actually see anything cross the event horizon because of this time dilation. But an observer who's falling in, they wouldn't notice anything special at the horizon. They just keep falling.
It's all about perspective.
Yeah, exactly. Two different observers see completely different things because of how space-time is warped near the black hole.
It's like relativity all over again, right? Different perspectives, different realities. Okay, so to help us visualize all this, to really wrap our heads around it, physicists use space-time diagrams, right?
Yeah, they're incredibly useful tools.
Mm-hmm.
For a non-rotating black hole, you'd have the singularity on one side, the event horizon as this boundary line. And then you have these light cones, which show what can influence what and the possible paths you can take in space-time.
So the light cones get distorted near a black hole.
Oh yeah, big time. Far away from the black hole, they're normal, that 45-degree angle representing the speed of light. But as you get closer to the horizon, they start to tilt inwards towards the singularity.
So it's like they're getting sucked in.
Yeah, kind of like that. And the light rays that fall in, they appear to get closer and closer to the horizon, but they never actually cross it, not in a finite amount of time.
That's what bothered Einstein, right?
Yeah, that apparent barrier that nothing could cross. But the thing is, space-time diagrams are like any map. They're trying to represent a curved surface on a flat piece of paper.
So they distort things.
They have to. Just like a map of the Earth distorts the continents. Different map projections preserve different things. Some keep angles accurate, others keep areas accurate. It's all about what you want to show. And with space-time diagrams, different coordinate systems can reveal different aspects of the black hole.
So like a different way of drawing the map.
Exactly. The original Schwarzschild solution used coordinates that made it look like there was a singularity at the horizon. But that's not actually a physical barrier. It's just a quirk of the math. If you use different coordinates, that singularity at the horizon disappears. It becomes clear that things can cross into the black hole.
Okay, so you're saying it's just an artifact of the way the math was done.
Right. It's not a real physical singularity.
So is there like a better way to visualize this whole space falling into a black hole thing?
There is. The waterfall model is a good one. Imagine space itself flowing into the black hole, like a waterfall. As you get closer to the horizon, the flow gets faster and faster. And anything near the black hole, like light, has to fight against this flow to get out.
Oh, I see.
Yeah. And the closer it is to the horizon, the harder it is to escape. It's like trying to swim upstream against a current that's getting stronger and stronger.
Okay, that makes sense.
At the horizon, space is falling inwards at the speed of light. And once you're inside the horizon, it falls in even faster. So Oppenheimer was right. From far away, you never see anything cross. But if you're falling in, you don't notice anything special at the horizon.
It's just continuous falling.
Pretty much, yeah, until you hit the singularity, that is.
Yeah, about that. There are these other diagrams, right, that are even more mind-bending.
Oh, absolutely. We've got Kruskal's diagrams and Penrose diagrams. They're like super maps of space-time. They let us see the entire history and future of a black hole and even how it might connect to other things.
Okay, so walk me through these. First, the Kruskal's diagrams.
So these are really cool. They're a mathematical transformation of the usual space-time diagram. The clever part is that in a Kruskal's diagram, all light rays, no matter the curvature of space-time, travel at 45 degrees.
So it makes things a bit simpler to visualize.
Yeah, definitely. And in these diagrams, the singularity of the black hole isn't a point in space anymore. It's a curved line that represents a moment in time. It's like the ultimate future for anything that falls into the black hole.
Okay, I think I'm getting that. What about Penrose diagrams then? They sound even crazier.
They're like taking the entire universe, the infinite past, the infinite future, all of space, and compressing it onto a single compact map. And again, light rays always travel at 45 degrees.
That's pretty neat.
It is. So in a Penrose diagram for a non-rotating black hole, you've got the infinite past at the bottom, the infinite future at the top, and spatial infinity, like all the points infinitely far away, squeezed onto the sides. The black hole singularity is a horizontal line at the top, the end of time for anything that crosses the event horizon.
So it's like the ultimate destiny.
Yeah, pretty much.
And you can actually see that in these diagrams.
You can. The real power of these diagrams is that they show you the causal structure of space-time, what can influence what, and all the possible paths you can take. And once you cross the event horizon, you can't get back out. You can still receive signals from outside, but you can't send any back.
So it's truly a point of no return.
It is.
All right, so deep breath. We're going even deeper now. White holes.
Ah, yes. White holes.
So if a black hole is where everything goes in, a white hole is like the opposite.
You got it. A white hole is a region where things can only come out. You can't enter a white hole.
That's strange. How is that even possible?
It's a mathematical possibility that comes from the fact that Einstein's equations, they don't really care about the direction of time.
Time is relative. Again?
You got it.
Yeah.
If something is a valid solution to the equations going forward in time, then often it's also a valid solution going backward in time.
So a black hole running in reverse, that's a white hole.
Basically, yeah. You flip the direction of time in the equations and you get a white hole.
So instead of everything getting sucked in, it's like everything's being violently expelled outwards.
Exactly. It's like a cosmic fountain spewing out matter and energy.
Wow, okay. But do these things actually exist?
That's the million-dollar question. We've never observed one, and there's no clear way they could form in our universe.
So it's just some mathematical idea for now.
For now, yeah.
Yeah.
But it leads to other intriguing possibilities.
Like what?
Wormholes.
Ah, yeah. The bridges through space-time. Tell me about those.
So if you look at the maximally extended Schwarzschild solution, that's the complete mathematical description of a black hole. It's just that there might be a connection between the inside of a black hole and another region of space-time.
Like another universe.
Possibly, yeah.
Okay, so we're talking like interdimensional travel here.
Potentially. These connections are called Einstein-Rosen bridges, or wormholes. They're like tunnels through space-time.
Yeah.
And they're formed at the event horizon of the black hole.
So could you, like, jump into a black hole and end up in another universe?
Well, the math says it's possible. But these wormholes, based on the Schwarzschild solution, they're incredibly unstable. They pinch off almost instantly.
So you wouldn't even have time to blink.
Not even close. And plus, if you look at the light cones on a Penrose diagram, they don't point towards another universe. They still point towards this singularity. So you need to travel faster than light to actually use one of these wormholes, which isn't possible.
So they're like dead ends.
For all practical purposes, yeah. But it gets even more interesting when you consider rotating black holes.
Ah, right. Black holes aren't just sitting there, they spin.
Exactly. And almost all stars rotate, so when they collapse, the black hole they form also rotates.
That makes sense.
And the math for rotating black hole, that's the Kerr solution, discovered by Roy Kerr in 1963, is much more complex than the Schwarzschild solution for a non-rotating black hole.
More complex? Like how much more?
Oh, it's night and day.
Yeah.
And this added complexity leads to some really interesting structural differences.
Like what?
Well, rotating black holes, they're not spherical anymore. They bulge the equator because of the centrifugal force in the rotation.
Kind of like the Earth.
Kinda, yeah, but more extreme. They also have this region called the ergosphere, just outside the event horizon. Space-time is dragged around so fast in the ergosphere that nothing can stay still.
So you're forced to move?
Yeah, you can't just hover there.
Right.
But you can still escape the ergosphere. It's not a one-way zone like the event horizon.
Okay, but once you cross the event horizon of a rotating black hole, that's it, right?
Well, it's more complicated than that. Rotating black holes have two event horizons, an outer one and an inner one. And the inner horizon, that's where things get really weird.
Where? How?
If you cross the outer horizon, you're still being pulled in. You can't escape. But once you pass the inner horizon, the math says you enter a region where you can move again. You're not doomed to the singularity anymore.
Wait, really?
Yeah. And the singularity itself, it's not a point in a rotating black hole. It's a ring.
So you could, like, potentially fly through the singularity?
Theoretically, yeah. If you approach it just right, you might be able to pass through the ring without getting crushed.
This is getting wilder and wilder. Okay, so what happens to the Penrose diagrams for rotating black holes? How do they show these new features?
They get even more complicated, of course. The singularity isn't a straight line at the top anymore. It's lifted to the sides, and that opens up this whole new region inside the inner horizon. And the boundaries of that region, well, they don't necessarily lead to a crushing singularity or the end of space-time.
So where do they lead?
That's the big question, right?
Yeah.
Some physicists think that if you could pass through the inner horizon and maybe even the ring singularity, you could come out of a white hole into another universe.
Another universe.
Yeah. And there are even more speculative ideas, like an infinite chain of universes connected by rotating black holes.
Wow, that's a lot to take in.
It is. There's also this really out there idea of an antiverse.
Okay, what's that?
It's this hypothetical region with repulsive gravity. The math suggests that if you aim directly for the center of the ring singularity, you might end up there.
Repulsive gravity, like anti-gravity.
Something like that, yeah. It's all very theoretical, of course. But it shows the incredible range of possibilities that come out of Einstein's equations.
I mean, some of these things sound like pure science fiction.
They do. But remember, these ideas are born from taking the math seriously. Physicists are exploring what the equations allow, what the logical possibilities are.
Okay, so it's like pushing the boundaries of what we understand about reality.
Exactly.
But how realistic are these ideas, really? I mean, do we think there are actually chains of universes connected by black holes out there?
That's the big debate, right? And honestly, probably not. The problem is, these maximally extended solutions, they described eternal black holes in an empty universe. They don't account for how black holes actually form from collapsing stars.
So they're idealized.
Very much so.
Yeah.
And white holes, they're probably not real either. We've never seen any evidence of them, and there's no good explanation for how they could form.
So they're just a mathematical curiosity for now.
Most likely, yeah. And the inner horizon of a rotating black hole, that presents some serious problems too.
You mentioned something about infinite energy.
Yeah, the problem is if you imagine light continuously falling into a rotating black hole over an infinite amount of time, all that energy piles up at the inner horizon. And that would create its own singularity, a physical one, not just a mathematical quirk.
So it's like a wall, a barrier.
Exactly. It would block off any potential pathways to other universes that the math might suggest.
So all these possibilities, the white holes, the wormholes, the aniverse, they're just not possible.
Not with our current understanding, no. They might be mathematically allowed, but the real physics of the universe seems to get in the way.
Okay, I see. So what about creating our own wormholes then? For like interstellar travel, is that a possibility?
That's a different story. Morris and Thorne, back in 1987, they looked into the possibility of building traversable wormholes. No event horizons, so you could travel both ways, stable, so they wouldn't collapse, and you'd need a way to actually build them.
Sounds ambitious.
Oh, it is. But their work showed that general relativity, Einstein's theory, it actually allows for these kinds of wormholes. They can connect different parts of the same universe or even different universes, but there's a big but.
Okay, what's the catch?
You need exotic matter.
Exotic matter.
Yeah, stuff with negative energy density. That's the key to keeping a wormhole open.
So it's like negative mass.
Kind of, yeah. It's
Right.
a really weird concept.
Right.
And as far as we know, this stuff doesn't exist.
So no wormhole shortcuts for us.
Not likely, no.
Okay, bummer. So to wrap all this up, it seems like while black holes might hint at all these amazing things, white holes, wormholes, other universes, our current understanding suggests that they're probably not real.
Yeah, that's a fair assessment. The math is cool. It opens up all these possibilities.
Yeah.
But the physics, the real world, seems to put limits on what's actually possible.
It's like the universe teasing us with these amazing ideas.
I know, right?